Welcome, Earth and Space Science students, to the Dallas Independence School District STEM Environmental Education Center. If you are watching this and have not registered for this field trip yet, you can still do so by going to www.tiny.cc/EEC register to get yourself or your class registered for this field trip. We just use that information for our attendance purposes. And today's virtual field trip is going to be about the accretionary disk model. During this virtual field trip, students will explore the solar nebular accretionary disk model. We're going to start off with a discussion of accretion of planetesimals and protoplanets. Then we are going to compare comets, asteroids, and meteoroids. Next, we'll discuss the origin of the moon. And last, we're going to compare terrestrial to gas giant planets. While we're doing all of that, you can ask us questions. And the way you do that is you go to www.tiny.cc/EEC-question-answer, and you can ask us any question you like, and you can ask as many questions as you like. The more the better, and we will do our best to answer all of them for you. So let's get started with today's field trip with our first teacher. And I'm going to stop sharing my screen here so they can present.
Okay, that would be me. Hello, welcome to my classroom. I'm Miss Nash, and today we're talking about the solar accretionary disk model. And the thing about this whole process is that who knew that the universe was so dusty? But there's dust everywhere. All this pollen here. And of course, we always say we are made of stardust, and indeed that's true. So dust is really important. And accretion means things stick together. So if you leave something under your bed, you might go searching for it, and you might find little clumps of dust. I didn't bring any today to demonstrate, but we call them dust bunnies, and they're just all stuck together. And it turns out that that's what's happening all around us, out into infinite space. And so I'm going to show some pictures now, and of some really amazing photographs that have been photographs, and also some artist's conception of what's going on in outer space. Can everybody see that?
Yes.
Okay, good. So here we are in outer space. And according to nebular theory, stars form in these massive and dense clouds of hydrogen. Star-forming nebula. And these clumps can collapse gravitationally. So gravity is operating on this enormous scale. And some people think that it happens when it gets a kind of a bump in the start, when a supernova star explodes and gives a kind of a push to the cloud. But in any case, it forms what we call a protostar. And each protostar is surrounded by an accretion disk. So accretion disk. And it feeds that central star. And then as that, so we have things spinning around a cloud around that protostar. So a lot of swirling around, things collapsing, condensing, accreting, and they begin to form. They're in an orbital plane, kind of around like our planets are around our star, spinning around. So this is an actual, who knew there were frisbees and targets in outer space? So you see that disk around it. And then gradually in that disk, more accretion begins. It's sucking things in, and then gradually the bits of dust begin to stick together. And some of it gets shot out in these jets that go out along the pole of the planet, of the star. So you get this very thick accretionary disk around the planet. and around the star, rather. And all stars, protostars, have these disks around them. So the dust, again, tend to stick together and begin to form tiny 1 centimeter particles that gradually begin to form larger ones. More and more accretion. So again, you can see those rings around the new star. And these are the planetesimals. As they get larger, then they have their own gravitational attraction to the smaller bits around them. And then they can become larger and larger. They're very, very numerous, and they're spread throughout the protoplanetary disk. Some survive, some become aggregated to a larger one. And then we get something like this, okay, in which planets are beginning to form all around the star, the new star. So we think that asteroids are understood to be leftover planetesimals, gradually grinding each other down to tinier bits, and comets are thought to be planetesimals from the farther reaches of that planetary system. Meteorites are samples of planetesimals that reach the planetary surface, and they give us a lot of information about the early days of the solar system. So next time your mother tells you that it's time to dust, I want everyone to have a new appreciation of the importance of dust, because without dust, none of this would be possible. Okay, so thank you very much, and I'm going to turn it back over to Mr. Broughton for any questions.
Thank you, Ms. Nash. And the question that came in was, how do we know that that's how planets form? And what these are theories. It's no one could go back in time to see how the planets actually formed, but using what we know about the planets, scientists have come up with the theory of the accretionary disk model, and no, you still got to mute. You still got to mute yourself though. And anyway, so it's a theory that they've come up with, but it's a widely accepted theory. So we don't know for sure, but that is what we think. All right, now we're going to move on to Mr. Monroe.
Good morning, students. My name is Mr. Monroe, and my portion of your virtual field trip today is going to be dealing with an investigation about the characteristics of comets, asteroids, and meteors. And I'm going to start out with comets. Let's talk about the origin, their beginning. Well, what scientists believe is that they are leftovers from the formation of our solar system. Their origin is from the Kuiper belt and the Oort cloud. Now, when we talk about the Oort cloud, that started out as a theory saying that comets are also cosmic debris, probably planetesimals that originally resided in the vicinity of the orbits of Uranus and Neptune, rather than in the warmer regions of the asteroid belt. Thus, the nuclei of comets are icy balls of frozen water, methane, and ammonia, mixed with small particles or small pieces of rock and dust, rather than the largely volatile freestones and irons that typify asteroids. In the most popular theory, icy planetesimals in the primitive solar nebula that wandered close to Uranus and Neptune, but not close enough to be captured by them, were flung to great distances from the sun, some to be lost from the solar system, while others populated what has become a great cloud of cometary bodies, perhaps 10 trillion in number. Such a cloud was first hypothesized by a Dutch astronomer by the name of John Hendrik Oort And so thus began the Oort theory. Now, when we look at the size of comets, they're about the size of a mountain without their tail. Tails can be as long as, you're not going to believe this, 100 million kilometers, okay? The composition of comets is ice, dust, and small rocky particles. Parts of the comet include the nucleus, which is a solid inner core, the coma, which is the cloud of dust and gas, and the tail, which is gas and dust, can be seen as the sun heats the comet and blows it away from the sun. Comets' tails always point away from the sun as the solar winds blow the tail away, okay? Comets orbit in a long, narrow, elliptical path around the sun. Now I'm going to go to asteroids. You know, asteroids, their origin is the asteroid belt. And that belt is located between the planets Mars and Jupiter. They're made out of rocky objects left over from the formation of the solar system, and their size is a little bit smaller than a comet, ranging from 1 kilometer to 300 kilometers in diameter. In fact, there are some scientists that believe that asteroids, or an asteroid, was the cause of the extinction of the dinosaur. Asteroids move in a very elliptical orbit. Some of the largest asteroids known are Pallas, Juno, and Vesta. Now I'm going to go to meteoroids, or meteors. And meteors are just, their origin is actually bits and pieces broken off from comets or asteroids. And they're made out of dust and rocks. They're smaller than comets and asteroids. And one of the best things that I can remember that happens is that we get these meteor showers, and the Perseid is one of the meteor showers that has been observed for 2,000 years. And when I was very small, I used to hear people say, oh, there goes a falling star. And then I also had people tell me, did you make your wish? Wishing upon a falling star. And at that time, I was very young. I believe what I saw streaking through the sky was actually a star falling. And it wasn't until I got a little older in the upper grades and started studying that those were actually meteorites. And they happen pretty regular. So they go by the AKA a falling star. Okay? Now, that streak of light made by a meteor is usually by one entering the Earth's atmosphere as it begins to burn up. And meteorites do hit the Earth. We have learned a little bit about outer space from the residual, or what's left over that meteorite. And I'm going to close out right now. And hopefully I've been able to give you a little bit of information about the difference between a comet, an asteroid, and a meteor. So I'm going to turn it back over to Mr. Broughton, and just maybe if you have a question, he'll be able to answer that for you. I want you guys to have a good day the rest of the day. And thank you for your time. All right.
Thank you, Mr. Monroe. The question that came in is, can we see some pictures of asteroids, meteoroids, and comets? And yes, you can. Let me share my screen with you here. This is how comets look. So you can see they have a that fiery tail. They orbit the sun like asteroids do, but asteroids look like this, just giant rocks. They're smaller than a planet. You can see there's an asteroid belt in between Mars and Jupiter. And then meteoroids, well, let me close that so you can see a little more, look like that. And those burn up in our atmosphere and sometimes can actually reach the surface of Earth. But mostly they burn up in our atmosphere when they fly through it. And so there's your pictures. And if you want to see more, just do like I did and Google meteoroid, click on images, and you can look at as many pictures of meteoroids as you like. All right, now we're going to move on to our next teacher, Mrs. Fuller.
Good morning, students. We're going to be talking in this segment on how the moon formed. Now, before the astronauts went to the moon and made samples, took samples from the moon, there were three basic theories on how the moon formed. The first one was called the capture theory, and that idea was the moon was already formed and the gravitational pull of the earth was so irresistible, it was able to capture the moon and put it in orbit around the earth. The second one is the co-formation theory, and that theory stated that the moon and the earth formed at the same time, and the moon, being the smaller of the two, began orbiting the earth. Then the third one is called the fission theory, and the fission theory stated that the earth was so big as it began to rotate, it threw off material as fission. It separated from the earth. So one of the primary goals of the Apollo missions were to answer this question, or at least come up with a theory, or perhaps even reinforce the three theories, or one of the three theories that the scientists had about the formation of the moon. Well, they got there, they collected their samples, and they came back, and they found out, the scientists that studied them found out that the rocks were 4.4 to 4.5 billion, not million, billion years old. And that's older than any rocks we had here on Earth. And these rocks were called anorthosites. And there was a tremendous amount of study that went into this. And what they came up with after studying the makeup of the rocks, they came up with a fourth theory. And this is the most popular theory right now. It's called the Great Impact Theory. And this is what they think happened. They think as the Earth and the other planets had formed or were forming and were orbiting, revolving around the sun, that there was a small planet. They've named it Theia. Theia was the goddess who gave birth to the moon. So the scientists took that Greek goddess Theia and named this little planet it. And they said that it was so close to the earth, it actually knocked into the earth and it exploded Theia. But it also knocked a hunk of material. And by this time, the earth's crust had already begun to form, and it formed the moon. Now, it formed through something called accretion. And remember, that's the title of our program today, is the accretion disk theory. So what we had all these pieces of earth crust floating around out there, and they began to accrete. As they floated around, they bumped into each other, and as they bumped into each other, they began to stick to each other, and the heat generated caused them to get melted, and then they just all stuck together. And that's kind of what accretion is the gravitational pull. Everything has gravity. You and I have gravity, but these are bigger pieces, well, most of them. And so then we've got the moon, and the moon, of course, was in the gravitational pull of the earth and began to orbit the earth. So that's the Great Impact Theory right there. Now, as the moon was orbiting the earth, we were bombarded by pieces large and small from this formation process, and it made huge craters on the moon. So here is our model of the moon, and I'm going to show you one of the large craters. It's right here, and it's called Mendeleev. So a lot of these huge craters, the really big ones, have names and are named very often after the person who discovered them or to honor that person. We've got one named Secchi after the astronomer, the Italian astronomer who invented the Secchi disk. So these huge craters stopped being formed about 3.8 billion years ago, and then in the time that has elapsed since then, smaller craters have been formed on the moon because there's not a lot of geological activity on the moon, and there's no weather and there's no life to change the face or the surface of the moon. So these big craters are left over from 4.5 billion years ago. And so it gives us insight into the geologic past, or the lunar past, I guess I should say, of what was going on. Now, we get hit by asteroids, as you know, about the dinosaurs, etc., and we were being hit by these big particles from outer space also. But we have a very dynamic Earth that changes quite a bit. We've got a lot of erosion. We've got a lot of volcanic activity. We've got tectonic plates that move and shift and go under the sublimate underneath the continental crust. So our planet has changed tremendously, but the moon is essentially a historical document, and we can look back 4.5 billion years ago. When the moon first formed, it had a magma ocean caused by all these things that were hitting it. And one of the things that's very interesting about the moon is it has very little iron in it. But it and the Earth both have a lot of oxygen. So most of the iron in the Earth is in our core. So when Thea knocked into the Earth, it knocked crust off. It didn't hit us straight on and break the planet apart, but caused a side or a part of the Earth to break off. And this was crustal material, not core material. If you have, this is a fascinating theory. I encourage you to look it up and read more about it. If you have any questions about the giant impact theory, Mr. Broughton will be glad to answer those questions. Thank you.
Thank you, Mrs. Fuller. And the question that came up was, what is the difference between a hypothesis and a theory? And a hypothesis is a more tentative statement. It is testable. And so if you form a hypothesis, you can conduct an experiment, and then your hypothesis will be supported or not supported by the evidence that you gather during the investigation. A theory is a hypothesis that has been proven true or it's been supported over and over again for years under various conditions by many different scientists, usually all over the world. And once a hypothesis is supported over and over and over again, it can become a theory. Now, theories can change as we get new information and technology, but they're more, I guess they're more reliable than a hypothesis that hasn't been tested as many times. And then one other question that came up was how big are comets and asteroids and meteors? And I'm going to share my screen here to show you one example of that. Oh, there we go. So what you were looking at there is a comet. And next, now this is just an artist rendition. That comet is not really there because right down here is the city of Los Angeles. But to give you an idea of how big that comet is, the city of Los Angeles is one of the larger cities in the world. About 4 million people live there, not counting the suburbs. And the city of Los Angeles is about 500 square miles. So comets are really big. They kind of look small in those other pictures I showed you because compared to planets, they're small, but they're actually quite a bit larger than you might realize. All right, now we're going to move on to Mrs. Ramirez.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be comparing terrestrial planets with the gas giants. So if we take a look at our little diagram here, we have our rocky or terrestrial planets. Then we have the asteroid belt, which kind of separates our rocky planets from our gas giants. Another name for gas giants is simply the Jovian planets. And the reason they get the collective name as Jovian planets, jovial is just referring to the Roman god, and that was named after Jupiter. So today we're going to be comparing the characteristics between rocky and the Jovian or gas giants. So we're going to go ahead and start off with just a quick comparison, and then we're going to share my screen so that we can explore the solar system using an interactive planet model. So the first thing that we're going to talk about, we are going to look at the differences in size. So just by looking at our little example here, we can tell that the rocky planets are generally much smaller in comparison to our gas giants. And as we can tell, gas giants, as their name implies, they are generally more massive. And as we notice, the further away we get from the sun, the bigger the planets get. So that affects the temperature of these planets. So our rocky planets are generally going to be a lot warmer because they are closer to our sun. And then the gas giants, or those Jovian planets, are going to be much colder because they are further away from the sun. The next quick characteristic that we're going to look at is their density. So generally, the rocky planets are going to be more dense. They have a more solid core and solid surface. The gas giants are going to be less dense. It's hypothesized that they probably have a very small, solid core, but the rest of it's going to be all gas. And then the structure. So our rocky planets, as I said before, have a solid core. They have a solid surface. So if you think of our planet Earth, we have a core, we have a surface that we can stand and walk on. They're going to have fewer moons, and they have no rings. Now, if we take a look at our gas giants, a lot of people don't realize this, but all of the gas giants actually have rings. It's just the rings of Saturn that are the most beautiful and most noticeable, but all of the gas giants have rings. They're just a little bit more faint. So our gas giants, again, we think they might possibly have a small solid core, just like our rocky planets. They have no solid surface, so they have a very thick atmosphere. They have many moons, and they all have rings. Now, we're going to go more in depth over each of these planets using our internet website. So I'm going to present my screen, and we're going to take a quick flyby through all those planets. The website that we're going to be using is called Solar System Scope, and it's really cool because it's really interactive, and it allows you to kind of move around and see the interior and exterior of each of these planets. So when I was a kid, the way that I learned my planets, the way I learned them in order was using a very simple mnemonic, and that is, my very excellent mother just sent us nachos. So we're going to start with the planet that is closest to the sun. And we all know that that is Mercury. So I'm going to click on Mercury, and we're going to do a quick exploration of it. So here is Mercury, and it might take a little bit for us to zoom in on there. It is our smallest planet. It is just slightly larger than our very own moon. Now, it is the planet closest to the sun, but it is not the hottest, and we'll talk about that in just a second. It has super long days, so it has a slow rotation. But it does have also very short years. So it rotates once every 88 days, and it revolves once. So let's take a look at the structure. We were talking about the core earlier. So the core of Mercury is mostly molten iron, as we can see here. We have a mantle made of silicate rock. and then we have the crust, which is also silicate rock. So you can make comparisons. I'm pretty sure y'all are familiar with our own structure of planet Earth, where we also have a core, mantle, and crust. So that is Mercury. We're going to go back. We're going to take a look at our next planet. So again, we said very. Before I leave Mercury, though, I just want to talk about, hopefully you guys noticed the craters that were on Mercury. So just like our own planet, just like our own moon has craters, Mercury is filled with thousands of craters as well. It also has a very thin atmosphere. So it has an atmosphere of oxygen, nitrogen, sodium, hydrogen, potassium, and helium. And it has no moon. So remember earlier we were saying that a lot of our rocky planets, they have very few moons in comparison to our giant gas planets. So that is Mercury. We're going to go fly by to our next planet, and that's going to be Venus. Venus happens to be my favorite planet. Was named after the goddess of love. We're going to take a look at its cool surface. One of the reasons I like it so much is because it seems just like a very destructive planet. It's covered with lots of volcanoes. It is the hottest planet. It is over 900 degrees Fahrenheit. So even though it is not the closest to the sun, the reason why it is the hottest is because it has a super thick atmosphere of carbon dioxide and sulfuric acid, and it creates like a greenhouse effect. So when we trap all those gases, the heat intensifies and it traps that heat. And that is why this is actually the hottest planet. And it just has this very cool volcanic landscape. So to me, this is just the best planet. It also has no moons. And it's considered Earth's twin because they're about the same size. And if we take a look at its structure here, we see it does have an inner and outer core of iron and nickel, a mantle of silicate rock, and a crust that's made out of similar materials as well. So we're going to go to our next planet. So we had my very excellent. You guys should be familiar with this planet because we live there. This is planet Earth. It is also another terrestrial or rocky planet. And terra just means land, so that's where terrestrial comes from. So let's take a look at planet Earth. More than 70% of planet Earth is covered in water. As far as we know, it is the only planet that can sustain life. And we just think it's because it's in a perfect zone. So some people might call it like the Goldilocks zone. It's just the right distance away from the sun, that it's not super hot and it's not super cold. So that's what they mean by the Goldilocks zone. And here's my little plug. It is the only planet that can support life, which is why it's important that we take care of our natural resources, because as far as we know, this is the only planet that can support life. So we need to be respectful of all of our living plants and animals and resources that we utilize. We all know that it takes about 24 hours to make one rotation, and it's about 365 days for one revolution or go around the sun. It is a rocky planet, and its atmosphere is mostly nitrogen. There's also oxygen and about 1% of some other gases as well. And we have one moon. And something that I found while I was doing some research, the first being to ever orbit Earth was a female terrier mix, and that was in 1957. And I'm trying to show you guys this picture. I don't know where my camera view is, but this was a cute little picture of the little terrier dog that they sent out into space in 1957. And this was the first being from Earth that actually was able to go out into space. Now, unfortunately, this little dog didn't make it home, but 2 years later, the Soviets sent 2 more dogs. And they were the first 2 dogs that actually went into space and then came back alive. So I was not aware of that, but I just thought that was a cute little dog that they sent out. So space exploration has come a long way. So let's take a quick look at the structure of Earth. We're probably all familiar with it. We have an inner and outer core of iron and nickel, so very similar to the other planets that we just looked at. We have a mantle and a crust of basalt and silicate as well. So we have my very excellent mother would be our next one, and that stands for Mars. We know Mars because it's that nice red planet. It gets its name because it's named after the god of war. And that red is from iron that's been oxidized on its surface. Now we notice that Mars has polar ice caps. So I don't know if I can get a view. There they are. So as I'm rotating around, these right here are polar ice caps. So it was once believed that there was probably liquid water at some point in Mars history. And that's why we have these ice caps. We now think those ice caps are mostly frozen carbon dioxide. Mars has a very thin atmosphere, and it's a thin atmosphere of carbon dioxide, nitrogen, and argon. And then there's small amounts of oxygen and water vapor as well. It does have 2 moons, and as I said before, it is that wonderful red planet because of those iron minerals that have oxidized, causing the soil to look red. Now let's take a look at its structure. Again, it looks very similar to the structure of our planet Earth. So we have the mantle and crust with silicate rock and basaltic rock, and then we have a core of liquid iron, nickel, and sulfur. So we have my very excellent mother, Just. So now we're going to start moving into our gas giants. And again, the thing that separates our line between the rocky planets and the gas giants would be that asteroid belt. So let's take a look at Jupiter. Oops. Switch our planet there, and let's go back to our solar system. So there's Jupiter. Jupiter is another cool looking planet. It is the largest planet that we have, and again, it is that gas giant. It has cloudy winds, and those clouds are made of ammonia, water, and then the atmosphere is mostly hydrogen and helium. So if you think back to our sun, which we see over here in the background, the sun is also made out of hydrogen and helium. It has a great red spot. Let me see if I can maybe find it as we're rotating around. There it is. So that great red spot is actually a giant storm. It's been raging for over 100 years. And if Earth was the size of a grape, Jupiter would be the size of a basketball. So that just shows you a ratio of just how massive Jupiter is compared to our own planet. And it has a very short day. So one day on Jupiter is only about 10 hours, but it has a very long year. So you'll notice that as we move further away from the sun, the length of a year is going to get much longer. And so for Jupiter, it has 12 years. It takes 12 years to orbit the sun. And again, scientists do think that it's possible that these gas giants might have a solid inner core. It's just going to be really small. And when I was in school, Jupiter at the time had the most number of moons. However, I believe it was last year or maybe the year before, scientists made some great discoveries. And since then, we now know that Saturn actually has the most number of moons. And I believe it was actually a student from Skyline that corrected me on that. So that's why it's important to always keep up to date with new technology and new science information, because things are always changing. So I learned something new that day. So we now know that Jupiter is up to about 75 moons, but who knows, with more advanced technology, astronomers might be finding more. And it does have a faint ring system. So let's do a quick look at Jupiter and its structure. Again, we believe it might have a dense solid core, and then it has a mantle that's liquid metallic hydrogen and helium, and then an atmosphere of hydrogen and helium here. So we have my very excellent mother, Just Sent. Saturn is going to be the second largest. What you see on my screen here are the 4 Galilean moons of Jupiter, and they were named after, of course, Galileo. So let's go back to our solar system and take a look at Saturn. So Saturn is the second largest planet. Again, it is a gas giant. It has thousands of ringlets of ice and rock, and this is the one that we most know because of those beautiful rings. Its atmosphere is mostly hydrogen and helium. It also has a very short day, but a very, very long year. And it has the most moons. It's now, I believe they're up to 82 moons that have been identified for Saturn. So that's pretty cool. So let's take a look at the structure of Saturn. We can see, again, they hypothesize that it does have a dense solid rock for its core. And just like Jupiter, you know, it has a liquid metallic hydrogen and helium mantle and an atmosphere of hydrogen and helium. So you can start to see similarities between the structures of our gas giants. And now we're going to move on to our next planet, Uranus or Uranus, however you want to say it. Let me see if I can find it. So there's Saturn, Pluto. We're going to rotate around. There's Neptune, and there it is. So we're going to go explore that one. Now, this one is also referred to as an ice giant. And this one is also a little weird planet because it actually rotates on its side. So scientists think that at some point in its history, something large must have smacked it and knocked it on its side. And so it kind of rotates like a barrel. And again, it is an ice giant. It has about 13 noticeable thick rings. It has about 27 moons. And most of its mass is hot, dense fluid of icy materials like water and methane. So it's that methane that gives Uranus this beautiful blue color. So let's take a look at its structure. Again, we see a very small solid core. Again, we believe that it is possible that these gas giants do have a solid core. It has a mantle of water, ammonia, and methane. Again, it's that methane that gives Uranus that blue color. And then an atmosphere of hydrogen, helium, and methane. So let's go to our last planet, and that will be Neptune. And again, these right here are just some of the moons. And where is Neptune? So there's Saturn. And this is just a cool little app because you can, right here, you can actually see that asteroid belt that's providing a nice division for us between our rocky planets and our gas giants. So let me go to Neptune. Neptune we consider the twin to Uranus because they're they have that nice blue color. So let's visit this one really quick. It is a very cold planet, so it's also known as an ice giant. It has supersonic winds, and something cool that I learned about this one is the windiest planet, and it has wind speeds of up to 1,200 miles per hour, and that is close to the speed of a fighter jet. It has super short days, so it only takes 16 hours to rotate once. And it has very long years. So it takes about 165 Earth years for Neptune to revolve one time around the sun. So as we move further from the sun, the distance is greater. So it's going to take longer for those planets to complete their revolution. And again, it is an ice giant. It's made out of water, methane, and ammonia. It has 14 moons, and it is our windiest planet. So now we're going to go back to our planet system. Again, I highly recommend you guys explore this website. It's solarsystemscope.com. I'm going to stop sharing our screen. And I just have a quick reflection question for you guys. We talked about terrestrial and the jovial planets. My challenge for you guys is to see if you can create a T-chart and just compare the differences between a terrestrial planet and a jovial planet. So see if you can come out with at least 5 differences between those two categories. And that is all I have for you guys today. We're going to pass it back to Mr. Broughton, and he's going to answer any questions.
Thank you, Mr. Ramirez. And the question that came in is, why isn't Pluto a planet? And I'm going to share my screen here just to share a couple of websites that I think do a pretty good job of explaining why Pluto is not a planet. This first one is from NASA Solar System Exploration. And it says right here, Pluto's classification as a planet has had a history of changes since 2006 per the International Astronomical Union's planetary criteria. Pluto isn't considered a planet because it hasn't cleared the neighborhood around its orbit of other objects. So a picture that I think illustrates that somewhat is this right here. You can see here this red line represents Pluto's orbit, and it passes through that Kuiper belt, and it hasn't cleared that neighborhood of its orbit of any objects. So that is why astronomers don't consider Pluto a planet. All right, now we're going to do a quick recap of what we did today. So during this virtual field trip, we explored the solar nebular accretionary disk model. We discussed the accretion of planetesimals and protoplanets. We compared comets, asteroids, and meteoroids, explored the origin of the moon, and last, we compared terrestrial to gas giant planets. Thank you so much for joining us this morning. We appreciate you spending the time to learn about astronomy with us. And we would like to know what you think about this morning's field trip. And you can let us know by going to www.tiny.cc/EEC feedback and filling out a short form to let us know how we did today. Have a great rest of your day, and we'll see you next time. Goodbye.